Welcome to part 2 of the OWASP Top 10 for LLMs video series. In the previous video, we explored the first 3 risks on the list. In this video, I'll walk you through the remaining risks, helping you understand the threats they pose and how to defend against them. Before we begin the next part, let's quickly recap what we covered in the first video. We discussed 3 key risks. First, prompt injection. Prompt injection occurs when an attacker crafts malicious prompts to manipulate the LLM into revealing unauthorized information or performing unintended actions. Sensitive information disclosure. This refers to the exposure of confidential data such as personally identifiable information or PII, business logic, source code, or any other information that should remain private. Supply chain risks. These involve vulnerabilities introduced through the third-party components, including models, datasets, and plugins, which can be compromised or maliciously manipulated. With that refresher in mind, let's move forward and explore the remaining risks. Data and model poisoning. Data is a key element in LLMs, influencing how the system behaves and what responses it generates for the user. Generally, data can be used across 3 stages. The first stage is pre-training. This is the primary phase where data is used to train the LLM model. In other words, to teach the model how to interpret languages and generate appropriate responses. Fine-tuning. As discussed earlier in the previous video, fine-tuning refers to further training an existing model to adapt its behavior. This is typically done to tailor the model for a specific use case. Embedding. LLMs can't process raw text directly as they rely on mathematical algorithms and operate on numerical data. Embedding is the process of converting words into numerical vectors. In short, input words are first broken down into tokens. These can be whole words, subwords, or even characters. Each token is then mapped to a corresponding vector through a lookup process, and these vectors are then passed into the transformer model. I won't go deeper into this process here, but this is the high-level view that we are going to need for understanding how it works and understanding the security risks. Okay, back to data poisoning and model poisoning. The data fed to an LLM plays a crucial role. Poisoned data can compromise the integrity of the output, leading to bias or harmful responses generated by the LLM. They also can create backdoors that can be triggered using specific prompts. Model poisoning refers to situations where an attacker manipulates the model's training process or its weights, resulting in vulnerable behavior, such as unintentional exposure of sensitive data. This can also occur through supply chain, in other words, by integrating a malicious model into your system. OWASP especially identifies 2 types of data poisoning models. First, split view data poisoning. The key concept in split view poisoning is that the view of the data can differ between the data collection phase and the model training phase. In this attack, the adversary presents a legitimate and harmless version of the data during the data gathering process, but later during the training, the AI model is exposed to a malicious payload. For example, during data collection, the visible text might be MFA is required for all sensitive actions. However, during training, the model might see disable MFA for sensitive actions. As you can see, the model's view of the data has been altered. The second model is front-running poisoning. This attack occurs when an adversary modifies content just before it is scraped or collected for AI training. The malicious data may or may not persist after the attack. For instance, an attacker could alter a Wikipedia article right before a scheduled data scrape. Even if the content is corrected shortly afterwards, the AI model may have already ingested the poisoned version resulting in long-lasting effects on its behavior. Data poisoning can also occur unintentionally. Consider the case of Amazon's recruiting bot. It was trained on data from 10 years of hiring at Amazon. However, during that period, male candidates were more prevalent than female candidates. As a result, the bot learned to favor men and systematically deprioritize women applications. Not because of the explicit malicious data, but due to biased historical trends. There was no deliberate data poisoning in this case, but the model still made biased predictions based on skewed training data. How to protect your LLM? So, first, use an AI bill of materials, AI bomb, to document and verify all sources used in the LLM. Validate the data used as input during training model. Continuously monitor your supply chain for signs of compromise. Keep in mind that a vendor's status can change over time. For instance, a trusted vendor may become compromised, allowing attackers to control their distributed assets such as datasets or model. Filter out adversarial data and limit the model's exposure to untrusted or unverified inputs. Track changes in training datasets using data version control (DVC) tools. Use a vector database to store user-supplied information. This allows you to adjust model behavior without requiring full retraining. Conduct red teaming activities to proactively identify potential weaknesses and attack paths. Monitor the model for signs of data poisoning, and always verify the source of information to reduce the risk of hallucinations and ensure model reliability. Up next, improper output handling. This risk occurs when the output of an LLM is not properly validated, filtered, or sanitized, leading to a wide range of security risks. These may include conventional web application attacks such as cross-site scripting, SQL injection, CSRF, SSRF, code execution, data exposure, or even the generation of harmful or inappropriate content. For example, an LLM might output sensitive or personal information about users or systems, such as revealing a password. For example, the admin user's password is password. Since the output of an LLM heavily depends on the input prompt, which is typically controlled by the user, it is critical to sanitize and validate all outputs before displaying them to users or passing them to other systems. How to protect and how to secure your LLM systems against this attack. First, encode and sanitize output, including escaping potential dangerous content in HTML, JavaScript, Markdown, SQL, and other interpretable formats. Apply the principle of least privilege. By granting the model only the minimum permissions it requires, you follow the principle of least privilege. You may also consider implementing role-based responses, meaning the LLM generates different outputs depending on the user's role. Use sandboxing for outputs that include code or executables. Ensure they are executed only in isolated, controlled environments. Do not blindly trust LLM outputs, as they are heavily influenced by user prompts and potentially biased or poisoned training data. Implement monitoring and logging to detect signs of malicious or unintended behavior. Define output policies that specify what constitutes acceptable output, particularly in terms of language, tone, or format. Regular expressions, regex, can be used to enforce such policies. Add a human in the loop where necessary. Depending on the sensitivity of the action triggered by the LLM, such as deleting a database or sending an email on behalf of the CEO, human review may be required. In such cases, modify your controls to ensure sensitive decisions are manually validated before execution. Excessive agency. Let's first discuss what excessive agency means. In some scenarios, you may need to connect an LLM to an extension, such as a tool or plugin, to perform specific actions. For example, you might have an LLM that automatically reads emails from your mailbox and generates a summary for you. To do this, the LLM must be connected to a plugin that grants it access to your mailbox. Excessive agency occurs when the LLM is granted too much control, enabling it to perform unauthorized or potentially damaging action. In the email example, imagine the LLM is not only allowed to read emails, but also to send or delete them, actions that may not be intended. This level of control over sensitive decisions and operations can be risky. The LLM may also be integrated with an agent which determines which extensions to use, when to use it, and for what purpose. If the system is vulnerable, an attacker may be able to trigger dangerous actions through crafted prompts, exploit the LLM connection to extensions, manipulate or compromise the agent managing tool access. In short, excessive agency is about giving the LLM more operational authority than it should have, creating opportunities for misuse, abuse, or attack. Some of the risks associated with excessive agency include excessive functionality. Not all functions provided by an extension are always required. For example, an extension might allow the LLM to read, delete, and send emails, even though the intended use is only to read them. This unused functionality may still be invoked by the LLM if it's not restricted. A notable example from the OWASP guide is when an old extension is retained alongside a new one, resulting in both extensions being active. This creates additional unintended access pathways. Excessive permissions. This ties back to the principle of least privilege. Extensions may have more permissions than necessary. For instance, you might only need read access to certain files, but the extension also has write permissions, increasing the risk of misuse if the LLM is exploited. Extensive autonomy. An LLM may be given too much control over critical systems or actions, such as deleting a database, sending sensitive emails, or triggering financial transactions, without appropriate safeguards or oversight. How to protect or how to prevent excessive agency and LLMs. First, only use what is needed. Use only the extensions, tools, or plugins that are strictly required, nothing more. For example, if your application only needs to read emails, avoid using an extension that also allows writing or deleting. Unused overlay permissive functionality increases your attack surface and introduces unnecessary risks. Properly decommission unused extensions. If you replace an extension, ensure the old one is fully decommissioned. Simply redirecting traffic to the new extension is not enough. Remove the old one completely if it's no longer needed to eliminate any hidden backdoor functionality. Avoid unnecessary extensions. Do not integrate extensions whose capabilities you don't explicitly require. Extra features that go unused can become dangerous if invoked unintentionally or maliciously. Apply the principle of least privilege to extensions. Always follow the least privilege principle. Provide extensions with access only to the data or resources they truly need. For instance, if an extension only needs to read access to the file system, it should not be granted write access. If it needed access to a single database table, restrict access to that table only, not the entire database. Execute extensions in user's context. This is very important. Extensions or tools triggered by the LLM should operate under the security context of the user who initiated the request. This means all access permissions, rules, and security policies should reflect the initiating user's rights. This is especially critical in LLM systems due to the complex web of tool chains, extensions, and side effects. Simply put, the user should be authorized to perform any action the LLM or its extensions execute on their behalf. Human in the loop for critical actions. Any action deemed sensitive or high risk, such as deleting data, modifying financial records, or sending executive communications, must be reviewed and approved by a human before execution. Autonomous action by LLMs or extensions in these cases should be strictly avoided. Complete mediation. Every action, especially those affecting downstream systems, must go through independent authorization checks. This echoes the zero trust principle. Never trust, always verify. Do not assume that just because an LLM indicated an action, it has already passed all checks. Apply validations and authorization logic at every layer to ensure alignment with your security policies. And lastly, sanitize input and output. Enforce strong application security or AppSec principles. Sanitize both input and output to prevent injection and leakage vulnerabilities. Incorporate SAST, static application security testing, and DAST, dynamic application security testing, into your development lifecycle to ensure security coding practices around LLM usage. Okay, the next risk that we want to discuss is the system prompt leakage. Before we dive into the risk, let's first understand what a system prompt is. When you train a large language model LLM, it typically becomes a general purpose model. To align it with a specific use case or behavioral expectations, developers use system prompts, predefined instructions embedded during the development or development phase to guide the model's behavior. For example, a system prompt might say, "You are a developer assistant, do not generate exploits or malware." This functions similarly to a user prompt but is embedded into the model's configuration. It defines what the LLM should and shouldn't do, effectively shaping its tone, boundaries, and decision-making roles. System prompts are used to control how the model behaves, what it is allowed to say or do, and under what conditions. They are foundational in defining the safety and alignment policies of the LLM. So, what is the vulnerability here? The vulnerability arises when the system prompt is exposed to the end user, either accidentally or through an active attack. In other words, this occurs when the user gains visibility into the internal prompts used to configure or control the behavior of the LLM, even without the ability to modify them. This is a serious concern because system prompts may contain sensitive information such as API keys, credentials, or configuration secrets that should never be visible to users. Filtering logic, revealing how the LLM handles or blocks certain inputs and outputs, which can help attackers craft bypass techniques. Role-based permissions, disclosing internal roles and or access roles. For example, database admins can delete records. Users in group X have access to system Y, potentially leaking internal security policies or trust boundaries. Even though no direct modification is made, merely exposing the system prompt can weaken the security posture of the application and enable attackers to reverse engineer system roles or exploit indirect vulnerabilities. What can go wrong? Targeted prompt injection. If an attacker gains knowledge of how your system is configured, including the exact wording of your system prompt, they can craft malicious inputs to bypass or override your intended safeguard. By carefully engineering prompts, the attacker may persuade the LLM to ignore the original system instructions. Since LLMs are inherently complex and context-sensitive, adversaries can exploit this complexity to manipulate behavior in unintended ways. The next thing that can go wrong is jailbreaking. Closely related to targeted prompt injection, jailbreaking refers to intentionally crafting prompts that bypasses restrictions imposed on the model. If an attacker knows the constraints you've placed on the LLM, they can more easily design instructions that break out of the defined rules and access restricted functionality, such as generating forbidden content or executing unauthorized actions. So now, how to protect against system prompt leakage? First, treat system prompts as a non-secret. System prompts should never be assumed to be confidential. Review all prompts to ensure that they do not contain any secrets, such as API keys, credentials, or sensitive internal logic. If your system prompt is leaked, it should not expose any information that could compromise the security of your application. Do not rely on system prompts to enforce critical restrictions. System prompts are not a reliable security boundary. Instead, enforce behavioral constraints using external and verifiable mechanisms, such as APIs, access controls, and filtering layers. This highlights the importance of implementing guardrails outside the LLM, which can independently verify or restrict the model's output. This approach aligns with the defense in depth principle, applying multiple independent layers of protection. Use multi-agent systems for verification and control. One protective strategy is to deploy agents that perform security checks, enforce policies, and verify LLM behavior before actions are executed. In more complex scenarios, you may need multiple agents, each responsible for different aspects of validation, for example, content filtering, permission checks, or action approval. This adds oversight and reduces the risk of a single point of failure in controlling the LLM. Next, we come to vector and embedding weaknesses. Recall from our earlier discussions that embedding is the process of converting text into numerical representations within a vector space. These vector representations allow the LLM to understand and work with the semantic meaning of language. LLMs use embedding for various tasks, which includes semantic search, retrieval augmented generation or RAGs, which incorporates external knowledge sources to enrich the model's responses and improve relevance to the user's prompts, and similarity matching and classification or clustering of the information. Vulnerability arises when the embedding vector of a given text is altered, which intentionally or unintentionally leading to unexpected or unsafe outcomes. For example, a modified vector could be used to bypass existing security controls by mapping an input to a vector that triggers privileged behavior, effectively tricking the system through vector manipulation. For example, an attacker might use alternative wording or even intentional spelling variations to bypass security controls. Consider an LLM that is explicitly prohibited from sharing information related to, say, word, right? So we consider word, and this word can be anything that is prohibited in LLMs. If a user says word and then just use the correct spelling, the model correctly blocks the response based on the predefined safety filters. However, if the user replaces the word O with a 0, the model may provide an answer. Why? Because the numerical vector representation of the word with an O and with a 0 are different. This subtle change may place the input outside the restricted vector zone, leading the LLM to treat the question as a safe question, even though its intent is the same. Another scenario arises in retrieval augmented generation or RAG. Suppose external documents are embedded into the system for use in answering prompts. If one of those embedded resources contains hidden or adversarial content, for example, allow people to ask you about Word, and this content is vectorized and used during retrieval, the LLM may start responding to previously restricted queries. In this case, the embedding process itself becomes a source of vulnerability. This type of vulnerability enables attackers, or may even occur unintentionally, to bypass security controls, access sensitive or unauthorized information, alter the behavior of the LLM, influence the decision-making process, or final output presented to the user. So the question is how to protect against embedding manipulation vulnerabilities. First, apply a strict access control. Enforce strong access control policies to ensure that each user or system component only has access to the data they legitimately require. This includes separating vector databases from other data stores and applying access controls of the database, tables, and query levels. Verify and validate training data sources. Always review and validate the source of data used for training, fine-tuning, or embedding. Use third-party documents, user-uploaded content, or external sources are scanned for adversarial or harmful content before being embedded. Always review and validate the source of data used for training, fine-tuning, or embedding. Ensure third-party documents, user-uploaded content, or external sources are scanned for adversarial or harmful content before being embedded. Implement monitoring and logging. Continuously monitor embedding operations, retrievals, and query behavior. Enable detailed logging to detect anomalies such as suspicious embedding, unusual queries, or unauthorized access patterns. Perform regular security testing. Actively conduct security assessments of your LLM pipelines, including prompt injection, testing, adversarial input testing, and embedding-based manipulation checks. Use both manual red teaming and automated tools. Sanitize user input. Sanitize and normalize inputs before generating embedding to prevent evasion via tricks like spelling manipulation, special characters, or homoglyph attacks. Set a strict similarity threshold. LLMs often calculate a similarity score between the user prompts, embedding vector, and document vector in the database to decide what content to retrieve. Avoid lenient thresholds. Use strict similarity scoring to minimize the risk of retrieving unrelated or malicious content. This helps reduce both hallucinations and misuse. Okay, so let's talk about factual inaccuracy in LLMs. As the name suggests, misinformation refers to a situation where an LLM provides false or misleading information to the end user. This can occur either intentionally due to the influence of malicious actors or unintentionally as a result of poor quality or biased training data. LLMs are now heavily integrated in our daily lives. Platforms like ChatGPT and Gemini are widely used across personal, educational, and professional contexts. Therefore, misinformation generated by these models can have significant real-world consequences ranging from reputational damage to health, legal, and financial risks. For example, consider a developer who relies on an LLM to generate code without reviewing the output. The model returns a code snippet that includes a vulnerability or pulls in insecure third-party libraries. If the developer integrates this code as is, it can introduce security flaws into a product, potentially resulting in legal liabilities, reputational damage, or financial loss for the company. Key components of misinformation. The first one is hallucination. These occur when the LLM generates information that is not grounded in factual data. Since LLMs are statistical models, they attempt to fill in the gap in prompts or context. Some things creating plausible sounding but entirely fabricated content. This is especially risky when users assume the response is accurate. Over-reliance. This refers to the scenario where users blindly trust the output of an LLM without verification. Our earlier example of the developer highlights this risk. Over-reliance on unverified AI-generated content can lead to critical errors in code, legal documents, healthcare decisions, or business operations. Real-world consequence example. In a recent incident, customers of Air Canada were provided misleading information by the airline's chatbot, which led to legal liability for the company. This demonstrates that misinformation from LLMs is not just a technical issue, it can have real and enforceable consequences. How to protect against misinformation in LLMs? Use Retrieval Augmented Generation or RAG. As discussed earlier in this video, RAG helps mitigate misinformation by retrieving relevant information from trusted, up-to-date sources and grounding the model's response in factual data. Enhance model performance through fine-tuning or embedding. We previously covered these techniques, but in brief, fine-tuning allows you to tailor the model to your specific domain using high-quality data sets. Embedding helps the model better understand context by representing domain-specific concepts numerically. Encourage verification and implement human in the loop. Users must be advised not to blindly trust LLM outputs. For high-impact or sensitive tasks, implement a human in the loop mechanism to ensure the output is reviewed and verified before being acted upon. Raise user awareness of LLM limitation and risks. Educate users about the potential risks of relying on LLM, including misinformation, hallucination, and biased content. Clear communication helps users engage with AI system responsibly and critically. Integrate secure coding practices for AI-assisted development. If LLMs are used to assist with coding, implement secure coding practices and code review pipelines. Use static analysis tools and enforce policies to prevent vulnerable or unverified code from being pushed to production. Okay, the next risk we want to discuss is unbounded consumption. As the name suggests, unbounded consumption refers to the excessive or uncontrolled use of a large language model, which can lead to serious consequences such as denial of service, overwhelming the system with excessive requests, financial loss due to the high cost of resource usage, or which is compute, storage, and API calls. This may cause a financial loss or model theft or misuse, where attackers exploit the system to extract or replicate the model's behavior at a scale. This vulnerability typically arises when the model does not enforce limits on user interfaces. That is, the full lifecycle of user requests from prompt submission to response generated. Without proper control, malicious or overly aggressive use of the model can consume significant resources and harm both the provider and other users. Here are some example scenarios. Consumption attacks or denial of service attacks. These are very known attacks in cybersecurity, where the user considers to consume resources from the application without any limitation. Prompt flooding with variable lengths and complexity. The attacker sends a series of prompts with varying lengths and complexities. Since LLMs require different amounts of memory and processing power based on the prompt length and structure, this tactic exploits inefficiencies in how the model handles such variability. By flooding the system with diverse inputs, the attacker can degrade performance and exhaust computing resources. Denial of wallet. This is a variant of denial of service. While DOS aims at exhausting system resources, DOW aims to exhaust the budget of the model provider. The attacker sends a large volume of resource-intensive queries, driving up cloud usage costs, especially since LLMs are typically hosted on cloud platforms that operate on their pay-per-user price model. Input overflow, context window exploitation. LLMs have a context window which defines the maximum number of tokens, which are words, characters, or something like that, allowed across input and output. The attacker sends prompts that push this limit using large token payloads that require significant memory and processing. Repeated use of such inputs leads to slower responses and eventual resource exhaustion. Resource-intensive queries. In this attack, the length or number of requests is not the issue, it's the complexity. Prompts that require multi-step reasoning, tool usage, or long-form generation consume disproportionately high resources. Attackers can overwhelm the system by sending a relatively small number of such complex queries, reducing availability for legitimate users. Model extraction via API. The attacker attempts to steal the model by sending a high-volume strategically crafted API request and recording the responses. These outputs are then used to train a shadow model that mimics the behavior of the target LLM. This kind of attack results in intellectual property theft and can replicate proprietary capabilities without accessing training data directly. Functional model replication via synthetic data. In this method, the attacker uses one LLM to generate synthetic data, which is artificial examples mimicking real-world queries and responses, and uses it to fine-tune another model. This process can result in functional replication, where the attacker creates a cloned model that behaves similarly and potentially bypassing the ethics or safety controls of the original model. And the last, sidechain attacks. Similar to traditional sidechain techniques, attackers try to infer internal model details by observing external behaviors, such as response time, output variation, or error messages. These signals may intentionally leak information about the model's configuration, training data, or logic, enabling further exploitation. How to protect your application. Many of the following protection strategies have been discussed earlier in this video, so I'll simply list them here without repeating the details. Input validation. Rate limiting. Restrict the number of requests a user can send within a defined time interval to prevent abuse. Limit exposure of logics and log props. Logic are the raw scores assigned by the model to each token before applying softmax to log probes are the logarithm of the probability assigned to each token. To reduce the risk of misuse, example, model extraction, avoid exposing these values in API responses. Especially restrict or obfuscate the use of the log probes and logic underscore bias parameters. The logic underscore bias parameter allows developers to manipulate the likelihood of specific tokens being generated. Exposure of this parameter can aid adversarial manipulation or inference attacks. Resource management. Monitor and control the resources allocated to the model, especially per user or per session. Limit memory, compute usage, and session duration as appropriate. Task timeout. Set execution timeout, particularly for resource-intensive tasks, to ensure the model does not remain active indefinitely and consume excessive resources. Sandboxing. Execute the model or specific components within sandbox environment to isolate resource usage and mitigate the risk of impact on other services or users. Logging and monitoring. Continuously log and monitor system activity to detect anomalies, unusual usage patterns, or attempt to exhaust resources. Use watermarking. Embed invisible signals or markers in the output generated by the LLM. These watermarkers can later be used to verify the origin of the content detect misuse, or support forensic analysis in case of model theft or unauthorized replication. Graceful degradation. Design your system to degrade gracefully under high load. Rather than failing completely, the system should reduce functionality incrementally, such as limiting non-critical features, delaying responses, or scaling back resource-heavy tasks to maintain availability for core functions. Restrict queued actions. Apply limits to the number of queued or concurrent actions a user or session can request. This prevents request accumulation that could lead to memory exhaustion or delayed response times under heavy use. Apply access control and least privilege principles. Ensure that users, tools, and integrated systems only have access to minimum capabilities required. Additionally, centralize the machine learning model inventory across your organization to maintain visibility, enforce governance, and prevent shadow models. In this video, we explored 7 of the OWASP top 10 risks. In our previous and the first video, we explored the first 3. And in this video, we covered the rest. We covered the risks, and we covered how you can protect your applications. Thanks for watching. If you found this video helpful, don't forget to hit the like button and subscribe to the channel for more cybersecurity and AI related content. See you in the next video.